1, 2, 3, 2008. Like this video if you were born 2008. How old would you be? 14? 14 doing Leetcode? That would be legit. So today we're going to do problem maximum earnings from taxi. Okay. Full disclosure, I haven't had a chance to look at this problem yet. So hopefully I can figure out the right approach to solve it in real time, and it'll give you an opportunity to kind of see someone walk through kind of the required steps and intuition required to solve these problems. Required. Okay, so there are endpoints on a road. You are driving your taxi on. The points on the road are labeled from 1 to N in the direction you are going. You want to drive from point 1 to point N, okay? To make money by picking up passengers. Apparently I can't read correctly. You cannot change the direction of the taxi, all right? The passengers are represented by a zero index 2D integer array rides, where ride I equals where the passenger wants to start, where the passenger wants to end, and the amount of money they'll give you tip. This is the ith passenger requesting a ride from point start I to end I, willing to give you tip $1. For each passenger you pick up, you earn end minus start plus tip dollars. Okay, so I guess I lose $1 for every point that I have to go, you know, spending money in gas. Right? That's why you should always tip your Uber drivers, because sometimes they're not even making that much money. It's quite a crazy world we live in, but that's not related to this problem. Given N in rides, return the maximum number of dollars you can earn by picking up the passengers optimally. Note, you may drop off passengers and pick up a different passenger at the same point. Okay, so how many passengers? You can only drive one passenger at a time, right? So you can't like, just because if you could pick up multiple passengers, right, then you would just pick up every single passenger, right? Because there'd be no reason not to. If there's no constraint, you only get more money by picking up passengers, so it makes sense that you can only pick up one at a time. I would expect in an interview, if it was like a FANG company, they might ask you this company where you look for one passenger, and then they said, what if we change the constraint to 2 or 3 passengers? So be aware of that. There might be easy ways to build on this problem and make it a little more difficult. But again, that's not directly related. So this is an interesting problem, right? Because this is something you would have to think about if you're a taxi driver, right? Like, if I pick you up and you're willing to pay me this and you want to go this distance, well, it might actually be better to skip you because you're making it problematic. Because if I skip you, the next person's going to pay me more to go a shorter distance. And right after I drop that next person off, there'll be a subsequent person that's available who will pay me even more. So it'd be more optimal if I chose the next person and skipped you. So this is definitely like an intuitive problem. You could see how this would apply in real life, which is always nice. But let's stop rambling and let's just go ahead and get into solving this problem. Okay, so we have n equals 5. So your car is going to start off at position 0. I don't know why I'm doing it like this. Let's do it differently. So position 0, 1, 2, 3, 4, and 5. And I'm going to draw a little car. And I'm going to ask you not to judge me for the car that I draw. That's actually not that bad. So you start off at position 0, right? And your goal is to get all the way to position 5. But on the way, you have these people, right? You have this person that is at position 2 and wants to go to position 5, and they're willing to pay you $4. Okay? So there's this person here at position 2, and they want to go to position 5, and they're willing to pay you $4. Damn, motherfuckers be cheap. Oh, shoot, I just cursed, and now I'm going to lose monetization. Not that I could even monetize my channel. And then there's this other person at position 1, and they want to go to position 5, right? And they're willing to give you $1. Okay? So obviously in this system, it's pretty clear, right, for this simple example, that you should skip this person because this red person's only going to give you $1 and take this person and take it down the path, right? So I think that's pretty simple, right? For a simple example, and that's what we can see here, right? We can pick up passenger 0 to earn 5 minus 2 plus 4 equals $7. Oh, I'm an idiot. I didn't even realize I can't even do some math. But that is irrelevant. The fact that I misunderstood something very simple. Anyways, so yeah, we would take this person and we would earn 5 minus 2 plus 4, right? So you get money for the distance that you go plus money for the tip that you get, which makes sense. You don't spend money for gas. There's no cost associated with that. So disregard what I said before, even though it doesn't really apply to the problem. It just shows you that I have no common sense. Okay, so I think an easier way to model this problem would be to look at each of these points as nodes in a graph or vertices. So if we looked at each of these points as vertices in a graph, and instead, the thing is if you take a person, you're stuck with that person until you drop them off, right? So if I take, let's recolor this so it's similar. So if I take the person that's at position 1, right? I have to keep them all the way till position 5, right? So it's kind of like, you can think of it as a shortcut, but it's really like I skip any possible people that I could pick in this realm, right? I skip them because I'm taking person 1. I decided that I'm going to take this person, and since I made that decision, I have to take them all the way to their destination and collect the points, right? So that means that if I take this person, I'm going to end up getting the 1 point that I get. Or if I take if I skip this person, well, what does that mean? That means that I can go to the next point and consider whoever's there. So you can think of each node as being a place, and each edge that's coming out of it, right? Each arrow that's coming out of that node, that place, are the people that you can take. And if you take them, you have to travel down that edge, right? If you take the people that are available at this place, you have to travel down that edge and end up at the next place where you can start picking up people and collect the money that you get from going down that link, right? So this link doesn't actually have value 1. It has value 5 minus 1 plus 1, right? Because 5 is this 5, 1 is this one, and this one, right? So it actually has that value, which is 5, right? But if you decide, no, what, I don't want to take this person, I can consider the next node, right? Because if I'm at a node, that means that I'm empty and I can take a person. The reason why I have to skip all of these nodes here is because I have a person, so I can't pick up another person. So that's one way you can think of it. Versus if I go here, I have to pick up this node, and I have 4 plus, I have 5, which is my end location, minus my start location, 2, plus the amount of money I'll get, which is 4, which equals 7. All right. So the obvious answer here, right, is, well, again, this is the same situation, right? So if I'm at any node, right, when I start at node 0, when my car is here at node 0, I can either take people, which means I have to skip a series of nodes, because being at a node means that the car is empty, that it's able to process somebody. So I can either skip whoever's available at the node, right? Skip who's ever available at the node, or take the person. Can do the same thing here, do the same thing here, and do the same thing here. Right, so this is a directed acyclic graph, right, or a DAG, which means that this is a prime candidate if you model the system in this way for dynamic programming, right? Because a DAG can be solved using dynamic programming, because since there's a direction to data, right? So something leads to something else, right? Something from 1 leads to a situation at 5. And since there's no cycles, I can always back propagate information, right? I can use a recurrence relationship to determine the most ideal situation. So the way that you would then process this problem using standard dynamic programming is by going through the system and determining what's the best thing I should do given what would lead me to this situation. So the best thing I would do for 0, well, I have nothing to lean on from the past So I would just go forward and I would gain 0 points. Let's say, okay, not the best thing, add 0. The best thing, okay, let's just say, how am I going to explain this? Okay. Most people from this point, you're going to know what to do because you're going to see this modeled as a DAG, right? Which is why it's difficult for me to explain where to go forward from here, because seeing it modeled as a DAG should give you the answer. But maybe to find a little bit of intuition, let's say that we were considering this as the end time. 5 is the end time. What would be the best thing to do if 5 was the end time, right? Well, if 5 is the end time, meaning 5 is a time where I drop somebody off, if I'm in this state, there's only 3 ways I could end up in this state. Does that make sense? Either I was at 4 and I skipped, right? So either I was at state 4 before and that's how I got to 5, or I took passenger 2 and I had to skip all of these links. So maybe this should be blue actually. Or I took passenger 1, which made me skip all these links, right? So that's the only way I could get to 5, right? So what would be the best thing to do at 5? Well, to get the most money at 5, let's do yellow. At 5, either I came from 4. So the best thing to do at 5 is to find out what's the best from going from 4, right, which is this state. Maybe we should do a different color. Make this all. I came from 4. Or whatever the best thing is going from 2, right, looking at this link, plus the amount of money that I would get from that, which is 7. Or whatever's the best coming from 1 plus the amount of money I'd get coming from 1. Which is basically saying, in this state, what is the best I could have done to get here? Right? Well, if this is my end time, well, I could have gotten here by just continuing to pass up on passengers. So looking at the previous state. Or it's the most money I could have gotten going up to 2 and taking that person, or going up to 1 and taking that person. That's at position 1. So I'm trying to think about the best way to describe that idea, right? Without just saying, well, if you look at this graph, right? If you know the best value here, if you know the best values all the way up to 5, you'll know what the best thing to do is if it's best to skip values, because this is, when you're looking at 5, if you had this information, then you would have all of these things filled. So you would know what the best thing to do is at a state, because you know how much you get for skipping, right? So if you know what the best thing is to do up to 2, and you know the best thing up to 4, you would know what's the best way to get to 5, right? Because you could look at the previous states, right? Because you know what's best up to then, so you'll know what's best up to now by basing it off of things that were best up to some previous sets of states. And how would I intuitively explain that within the context of the problem? I don't know. You're basically in a state like this, and you're thinking, okay, if I ended at 5, and I knew if I could look backwards in time when I'm at this state, and I knew, like, okay, I know how much money I had before I picked someone up at 2, okay? And I know how much money I had if I picked someone up at the person at 1, and I know how much money I had if I didn't pick up either of them, right? So I know how much money I had if I skipped that person, right? So this car is going down this path, right? And imagine that it skipped these people, right? It skipped these people and it went up to here at this end time, okay? But imagine it could look back in time, and it could, when it gets here, it'll know how much it got from skipping these people, right? It'll know just how much it got from skipping these people because it skipped them, and it went forward and passed through and got to state 5, right? But now that it's at this state, it knows what it missed out on, right? Because it knows what it would have gotten from 2 if it took that link, and it knows it would have ended up at 5. So it knows, like, either it missed out, right? If he got to the state and skipped them and said, oh shoot, I got here and I actually have less money than if I actually took 2, then it'll know it would have actually been a better idea to take 2, right? Because it knows what's up to 2. So the basic idea, I guess, is when you pass people and you get to the end state where you would have dropped them off, you would know if it was a good or a bad idea to not pick them up. Does that make sense? Right? Like, you passed up on a deal, and now that you're in the end state, you know if it was a good idea or a bad idea to pass up on that deal. So that's the basic idea of this problem. Since now you're in this state and you know how much you would have gotten if you just went to the previous state, meaning that you skipped 2 and 1, you'll have an understanding of whether or not that was a good idea or a bad idea, and you can populate what would have been the best for this system, given you know how much you would have gotten if you skipped the people that you could have taken, which is here, right? If you skip those people, you'd be here. And if you had taken those people, remember, everything is the maximum value up to that point. So then any future point, when you check a point that comes before, you'll know if it's optimal or not. So what's the recurrence relationship then? Okay, so the best thing, right, the highest, the most optimal, I'm just going to call it B for whatever reason, at some state X is equal to the maximum of the best thing of the state before X, right? Because the state before X is the state if you skipped the people, right? Because it could be the case where, imagine you had a system like this, right? And there was just a real generous passenger that gave you all this money at this state, and then a really stingy passenger who only gave you this much money at this state. When you're looking at this state, right, either you have the case where you took this passenger, or you skip this passenger and you're here. Well, obviously it's better here because you get all of this money. So it's actually better to take this state, the previous state, and disregard all the people that you could have taken that would end up here. For some reason, my eraser is not an object eraser. Okay. So you can either take in that person that skipped everybody, or you look at all the edges that go into this node, right? Because into X, there's X minus 1. And that has 0 benefit, right? Because that means you didn't pick anybody to get here. And then you have all these systems, you know, A, B, C, all these previous people. Maybe it'd be better, make more sense if it was like this. And there could be dots in between these. I don't know. Right? There's all these people that have links into X, which means these are all the passengers where you pick them up, and this is where you would drop them off. So this is where you would collect the money from their trip, right? And they have associated costs, you know, alpha, beta, whatever the hell that is. I forgot. I haven't taken a physics class in quite some time. I've been out of commission for a little bit, right? So then it's for all of these edges, you would consider how much money you would get from them, plus the best value at these states, right? So I'll just call that some previous state P. So the best of the previous state plus the amount of money you would get from the previous state, right? And how much money do you get from a previous state? Let's just write it out. So you're at a state X. So you'd have the tip money you get from the previous state plus the state that you're at, which is X, minus the state P, right? Because that would be the distance for each place where place goes into X. Sorry, this is some messed up notation. But basically what I'm saying is you would look at all the states for any state, right? So you have a state X, and you'd say you'd consider the previous state where you get 0 points because you're skipping over all the people that end here and all the people that have trips that end at this state, right? And if you do this from left to right, that means that you can pre-populate these best values, right? So you know what the best is up to this value. And then going forward, right, if I had additional nodes, right, before you process this node, you processed everything before it, so you have the access to all the best previous values. That's the general idea. Okay, so I've rambled enough about this, so let's go ahead and solve it. So, let's first create this best array. It'll be just 0 for everything, and then we'll do n plus 1 because there's an offset by n, right? Because a ride can stop at 5. And then we'll just keep track of all the times where there's an end time, because an end time corresponds to what? An end time corresponds to a system having a link into a node, right? This one goes from 1 and ends at 5. So that means that there's something pointing into 5, right? There's an edge pointing into 5 starting from 1. So if you wanted to think of it as a graph, you could do that too, and then has a weight associated with it. So maybe we'll just think of it as a graph. So we'll create this graph, and we'll just make it a default dict to save ourselves some headache. Well, I guess it could be a... Yeah, we'll do it a little bit better. Okay, so for blank in range n plus 1. Okay, and then we'll look at each... How does this work? So there's a start time, an end time, and a tip. So end and tip in ride. So we look at each ride, and then we say G at the end time. So the end time has an edge going into it. We'll append to that the start time, so we know which time this thing came from, so where I picked this person up, and then the value of the edge, right? And the value of an edge is end minus start plus tip, right? And I'm just directly taking that from here, right? End minus start plus tip. We look at each ride. We do this. We play this game. Okay. Silent ride home. All right. And then we just need to process these slots in order. All right. So we look at this state, then look at this state, then look at this state, and so on and so forth. So we'll look at each state. So we'll look at each state. So we'll call it end time in range n plus 1. We don't need to look at state 0 because there isn't really no state 0, so it's just this one offset idea. So the best time for any time is either the previous time. So the max of, well, you can either be the previous time, or it can be the time, the start time for any node that points to this node, plus the dollar amount that you get from it for each start time and dollar in G at this node time, right? Because this node, this G will have at any end time, right? At any end time, all the nodes that lead into it, and the amount of money you'd get if you took that person, right? So either you don't take any of the people, or you take one of the people and you get the amount of money for taking that person and all the best amount of money you could get right before you picked up that person. Now this could have a small error. Well, because, you know, it's common that you make little errors. Like I think I forgot to end this thing. Silent ride home. Okay. And then at the end, we just return whatever's the best at the end time. Now the thing that I'm worried about here is if it goes too far back. Blank for blank in range. Unexpected indent. That's weird. Oh, for some reason this got put there. Silent ride home. The thing is, I'm worried that, okay, no, start, it's never going to start before. And this will never be minus, no, never mind. So there's no worry where, like, you have a negative index and it tries to wrap around the array. I was worried that could happen. But I don't think that can. So this should be an m plus n time algorithm. Yeah, so it's more than fast enough. Again, you know, don't focus too much on this because you submit it again and you get something different. So what's the space and runtime of this algorithm? Okay, well, let's first look at, let's say that m equals the length of rides. See, this one's slower. You know, it can be all over the place. So let's not worry about that. And then length, and then n equals length of n. N equals n. N equals n, whatever. Just to, okay, so for time, so we need to look at each ride to create this, this graph, right, where we have all the n times there. So for terms of time, this is going to be O of m at least, right, because we have to look at each of the m rides. And then we have to loop through n spots, right, to check what's the best at each spot plot of land. So that's O of m plus O of n, so that's O of m plus n. In terms of space, right, so we get O of m from here because we have to look at each ride, and then we have to look at the range of n, and we do a constant constant operation that state. Well, do we? Because we have to look at each. What if all m point to 1? No, because at most you would look at m, and then you look at all the m. You would look at all of the m edges only once in this whole loop system. So it's O of m plus n. Okay, it's not O of m times n. Right, because although you're doing n operations and you're looking at the m edges that travel into any end node, you're never gonna have to look at an edge more than once, right? Because you only consider it when it goes into a node. So you only have to look at each edge once. So it's O of m plus n. Okay, and what about space time? What about space complexity? Well, we have to build a graph that's size n, and this thing is size n, so it's definitely n. And then we have to add each edge, which corresponds to rides. So that's m edges. So again, it's the same O of m plus n. So this is a linear time algorithm with respect to the inputs. So that's pretty cool. Thank you for watching. You can definitely make this a little shorter if you want to, but I've had multiple comments where people have suggested that I stop doing that. So this is probably as simple and not as short as I can make it. Thank you, thank you, thank you.